So today I'm talking about two different applications of Bogomolov instability. So remember, we're talking about S, usual thing, non-singular projective surface, and E, rank 2 vector bundle on S. And in different contexts we have this structure that I have a line subbundle and a quotient bundle. Right, so here, so I'm writing this as a Cartier divisor, L and M. Right, so who this IZ is, so what this means is that locally at any point, the E is O plus O. So locally, it's a rank 2 vector bundle. It's a locally free sheaf of rank 2, which means locally it just looks like O plus O. And this is mapping to something here which also looks like O. And this map is going to be given by F comma G. I think I want to write this. There's no good way of writing it. Let me write G. Let me write FG. Right, so these two guys, they're just two maps from O to O, so they're just locally defined functions. And then they're going to define an ideal in there. So Z is, IZ is just the ideal generated by this. Right, and then the co-kernel, if I write it like this, the co-kernel is also isomorphic to O, and it's just G minus F. Right. So given this situation, I can always assume that F and G have no common factors. That's just possibly change. If this F and G have a common zeros along the divisor, I can just sort of include that divisor as part of L. So I slightly changing L. I can assume that F and G have no common factors. Then this is called the Koshul complex of FG. Right, and the fact that it's exact is just saying that F and G have no common factors, and this ring O, the local rings O are locally unique factorization domains. Right, so there was a theorem. So in this situation, so I sort of stated this last time in a slightly muddled way. In this situation, the first Chern class of E is the class of the divisor L plus M. So this is a divisor class. So you can think of it as being in pic S, or in Néron-Savary group of S, or in H2 of S. It's with coefficients in Z. And I'm not going to really take the trouble to say which I need at each stage. Right, and C2 of E is L times M plus the degree of Z. Right, so you know, the way to think about this is if L is 0, then this means that there's an injective map there which has got exactly Z as its 0 locus. And so if I've got a vector bundle E and a section which exactly vanishes at Z, so Z is the locus generated by F equals G equals 0, where that's F and G is a way of writing this a section of a vector bundle, then the second Chern class is equal to degree of Z. It's just the number of zeros of a section. Right, and then, you know, if you have to twist it up and down a little bit, then you twist it up and down a little bit and calculate for a bit, and you get this. Yeah? So this is just to put you back in the picture of where we got to last time. And then there's this theorem that under these circumstances, C1 squared of E is strictly greater than 4C2 of E if and only if there exists a sequence, so O goes to OS of L, goes to E, goes to OS of M, this is supposed to be an IZ in there, goes to 0, where L minus M squared is greater than 4 times the degree of Z, and L minus M times any ample is greater than 0. Okay? So I explained, at least the idea of the proof should be clear. So let me just comment on the statement first. I've got this vector bundle, and I've got a sub-line bundle in it. So you know I can. So this first statement, L squared minus Z squared, is 4 degrees Z. That's basically just restating this thing here. So C1 squared minus 4C2 is if I try to get this right, as stated here, L plus M squared minus 4LM minus 4 degree Z. Right? So this is L minus M squared. These two terms together. L minus M squared. Right, so this guy is positive if and only if this guy is bigger than that one. Right, so this is just sort of basically trivial, just rereading the definition. However, so given that L minus M squared is positive, this means Riemann-Roch says either L minus M, either the divisor L minus M or it's or minus L minus M grows. So in the sense that H naught of n times L minus M is greater than a constant times n squared, where this positive constant. Right, so in that case we say that the L minus M is a big divisor. Some multiple of L minus M is bigger than any ample divisor, equivalent to saying this. Right? And so I have to choose one of these cases, right? And the statement is that if this happens, then there will be a sequence with this L minus M times the ample greater than 0. And so that means I'm in this case, that the n times L minus M grows like anything, grows is big, is as big as I want, right? So so the point is here, you know, if it will be it's easy to achieve this. This is not at all significant. Having a line subbundle of E which is very, very negative is no significance at all. You can always make that in any vector bundle. The point is here that that if I have this, then I have this destabilizing bundle here. I have this bundle here which is much bigger than 1/2 of E. So L is bigger than 1/2 of E. Right, and this is a strong destabilizing condition. So, you know, there are whole populations of algebraic geometers that work with in the study of vector bundles. And vector bundles with this property that there's a sub-bundle which is bigger than 1/2 of the bundle itself. This is these are called unstable, and they're sort of very, very special. Okay. So where am I? What applications do I want to do this? So I should say this is it. We're in characteristic 0. So just to remind you of the proof, I'm not going to say the proof in detail. I've got this guy P at PE over S. Right, so I could do PE over any bundle, over any scheme here, any scheme of dimension greater than or equal to 2. Right? Then I remember I defined this bundle B. So this is O of 2 tensor determinant of E to the -1. Right, so on this thing there's an O of 1. So here I've got E. I've got this O of 1, which is O of 1 on each fibre. This is a P1 bundle over every point. And this bundle here is O of 1 there. It's E viewed as the linear coordinates on this P1. Right? And then I make this combination here, which is invariant in a number of different ways. So this is the same thing as the relative tangent bundle of PE over S. Right, and the statement, the C1 squared minus 4C2 of E is positive, says that B is big. Right, so H naught of B, NB grows like n cubed. So again, there's a little positive constant so that it grows at least like n cubed. But on the other hand, if I take this B and I restrict to any surface FC, so this is inside P of E. So I have, here's my surface, here's the threefold P1 bundle over the surface. As if I take a curve here and just leave it restricted to this pullback, then I have this surface FC over a curve C. So this is just a rule surface, P1 bundle over the curve C. And then, so then B squared here, by this, just by construction, B squared on FC is 0. So this is a line bundle, and there's a big tension between two different things. One is this B squared is 0. B is, of course, positive on each of the fibres. It's O of 2 on each of these fibres, P1. But its square is 0. On the other hand, it's big. And that means it has to sort of move around in a big linear system. And these two things contradict each other. And the only way out of the contradiction is that there is a negative section in there. There's a section gamma with B times gamma negative. And then all of these sections of, all of these multiples of B have to vanish on gamma. They have to vanish on gamma many, many times. So that's the instability. Anyway, you untangle what this means, and you get out this conclusion. Right? And so, a point I was trying to make about this argument last time is that this is extremely coarse. Right? We're only talking about, this is like the proof of the index theorem I had. I have some statement that some multiples of this B grow arbitrarily to arbitrarily big as they can on a threefold. And then you restrict them to the surface, and you know there's something there which is 0 on the surface. So you have something on one hand which is very big, on the other hand which is equal to 0, right? And so there has to be a way out of the contradiction. The way out is that there's a negative curve here which sort of contributes some negative thing. B restricted to, you know, the thing that actually moves in B is B minus at least n copies of gamma. And then that can move around in a big system. So that's the statement, right? And so the surprising thing is this corollary. This was pointed out by Mumford. And maybe Bogomolov knew about it already. I don't know. So this first appeared in a paper of mine, but it was basically my reporting on Bogomolov's work, and together with comments of Mumford. So A is nef and big on S, and characteristic 0 implies that H1 of OS of minus A equals 0, or equivalently H1 of OS of KS plus A is 0. Right, so this is Kodaira vanishing. On S. So where's the logic come? And later on we're going to see also that things like H1 of MP times OS of KS plus A equals 0, except, and so on. So the other corollaries, the other immediate corollaries of this are to do with this Bombieri embedding theorem that I've been talking about for about 5 weeks. Yes. Okay, so let's try and understand this. So the first point is that this H1 of, well, either of these groups, I don't know which is the more, H1 of KS plus A is the same thing, is dual to X1 of OS of A OS. So you know, you need to, this is the same thing, KS plus A omega S. So if you take the statement of Serre duality written in terms of the H1 being dual to an X1, then I've got this omega S, which is the dualizing sheaf of the surface, and H1 of this sheaf is just the dual of X1 of that, right? And you know, what is X'd? So X'd is, extensions. And so, you know, you go back to wherever you read this, wherever you read about X or homological algebra or whatever, and you'll get that this is 0 goes to O, goes to E, goes to O S of A. Right. So, you know, what I mean, what I want is, if I've got an element alpha in there which is not 0, then I have a sequence like this which is not split. Right. So I'm really only using one element of this group. If this group is not 0, then it has some non-zero element, and I can write down a sequence like this. So, you know, the set of these sequences up to some equivalence is this set, and you know, you can worry about how you define the structure of additive group or of K module or whatever it is on this. But I really only want one single element of this group. Okay, so let me just explain this. You know, why is this? So you know, element alpha there, and I'm not really distinguishing between the group and the dual group. I don't really care. So I think, so you know, what does this mean? This means that this E, so locally, I'm just explaining, I'm making a little detour to explain how I get from an element of this to an extension like this. So locally, E is O plus O, and it's mapping O plus O is mapping surjectively to this OS of A. Right? So, you know, this is a locally free sheaf. So you go back to, you know, locally free, you know, it has this meaning that on an open set I can find a place where this is just isomorphic to OS of A. I can find a local basis of this. Right? So what I want is that this is locally split. Yes? So in other words, I can go to a small open set where this guy here is, it's a locally free sheaf. I can go to a place where it's a free sheaf. So choose a basis element there. Okay, then this is a surjective map of sheaves, and so if I restrict possibly to a slightly smaller open set, then this basis element, the basis element of this sheaf, is mapped onto by a section of this sheaf somewhere. And so I just choose a lift there, and that defines a lifting like that. So you know, if you've seen the definition in textbooks on commutative algebra, if you've seen projective modules are the same thing as locally free modules. And that's the assertion that any surjective map like this can be split. Right? If I've got a surjective map, I can choose a little splitting. So, so the extension corresponds to a family, let's say UI covering S and sections, you know, not let's say TI, alpha I, taking OS of A back up to this EA, curly E. Right, defined over U. Right, so you know this sequence is locally split, but not globally split, but not necessarily globally split. So if I now I ask why can't I just say, well, let's take the kernel and glue the kernel together as well in the same way. So then for if I do UI intersect UJ. Right, then I have a splitting over here and a splitting over here. It means here, on this thing, I've got UI, I've got this alpha I minus alpha j, and this is, if I could arrange for the alpha I minus alpha j to be always 0, then I would just have a kernel here, which is, then I could split the whole map. I could just change one alpha I to the to alpha I plus this difference, right? And so this thing ij, ui intersect uj, maps to alpha I minus alpha j, is a check cocycle. Right, and it's locally a section of OS of minus A, so it looks like a whole lot of elements in OS of minus A. So this difference here, UA minus UJ, is really a little locally defined in this piece, homomorphism from this sheaf, OS of A, into this sheaf OA, into this sheaf O. Right? So this means it's this alpha I minus alpha j is in H naught of UI intersect UJ of OS of minus A. So this is just hom OS of A into the kernel OS. Right, and that's exactly what that's so. And then you sort of worry about what happens if you change the covering and change the choices and so on, and then you get that this is so this alpha is in H1. So let's assume. So I'm trying to prove this theorem. So if alpha is not 0, then there exists a sequence like that. Right, and the E has C1 of E equals A, and C2 of E equals 0. Right, because it's the product of the first Chern class of this and the first Chern class there, and so it's 0 times A. Right, and so therefore C1 squared is greater than 4C2 for this E. So I'm going to do this diagram 3 or 4 times now. There is a sequence which defines the bundle E, defines the extension E. So this is so there's a 0 goes to O, goes to E, goes to IZ. Sorry, at the moment there's no IZ. Goes to OA. Right, and then there's the splitting. There's this unstable structure. So OS of L, IZ, OS of M. Right, and so they're both exact sequences. So at some point I'll just stop writing the end of the sequences. Right. So this row here, this is the definition. This is the construction of E from alpha, whereas this thing here is the given by Bogomolov instability. And so I want to get a contradiction from this. And you know, I have to say that each time I do this, I have a tremendous headache for several hours. So, I explained that you calculate the Chern classes of this. So the Chern classes of E are given like this, and that's by calculating this way. So on the other hand, I can also calculate this way. Right. So the first Chern class of E is L plus M, and the second Chern class of E is L times M plus the degree of this Z. Right, and so you know, the thing that we know for free is that L minus M squared is positive, and that L minus M times an ample is greater than 0. So now let's look at this sequence. I've got an arrow there and then an arrow there. So let's look at this arrow, this composite arrow. So let me call him, you know, I don't know, beta, for example. So the northeast arrow, beta there, from OS to L to OFA, can't be 0. Right, because if it was 0, then that would mean that this thing here is mapping into the kernel of that map, and the kernel of that map is E. Right, and so if this were happening, then if this were happening, then you know, this would just contradict this these statements here. Right, I would have that the O itself is bigger than the A. So that would follow from this statement. It would just contradict this statement. Right, else OS of L equals O.
If it is 0, it means that it factors through the kernel.
Yes.
If it factors through the kernel, it's the 0 map, because the kernel is O. If OS L goes into O, the only because you don't know that L is higher, of course. You don't know that L is positive. Yeah, okay.
No, L is not effective.
L
is big. L is bigger than E.
Yeah.
It's bigger than 1/2 of E, but we don't know that it's effective.
Yes.
Right. But we do know that this L minus M is so you know, I have to be a little bit careful and patient about this. So OS of L would be contained in O, and L minus M times ample is positive. Whereas O, so O 0 minus A is negative. Right, the A is well, it's nothing. A is nothing big. Okay, so this is then an inclusion of one line bundle in another. So then this means that OS of L includes into OS of A. And so this is multiplication by the equation of M. And then it follows from this that therefore M is effective. Or equally well you can say, if this map is not 0, it means that also this map is not 0. Well, because they're exactly the same argument. Otherwise, O and OS of L considered as subsheaves of A would just be identical. Right? So therefore, this map, so the M is some effective divisor, and of course it also has to pass through this Z. We're not going to make any use of the Z, but there's an arrow there. Right. It's a line bundle maps to another line bundle. It's a non-zero map.
It's non-zero, so it must be an isomorphic. You don't know if it's a map of line. Yeah, you can have some cokernel.
It's a line bundle maps into another line bundle. So it's one divisor is less than or equal to another divisor. So, this means that A is L plus M. And it's OS of L included in OS of L plus M. We're going to see the same argument 2 or 3 times, so it's worthwhile sort of thinking about all the issues involved here. So now we're going to get contradiction. It seems to me that each time I think about this, I get a headache. But I'm going to use these inequalities and the index theorem. You never get anywhere without the index theorem and the computation of C2 of E. So this is a kind of, at the moment I haven't written this out in a way where it's completely transparent. So let's just think about what the index theorem says. So I've got L squared, I've got LM, I've got LM and M squared, and L plus M is A. So L plus M all squared is positive, right? And so therefore the index theorem says that this little determinant is less than 0, less than or equal to 0. So L squared, M squared, less than or equal to LM, all squared. And also M is effective and A is nef. So I have A is L plus M, and so therefore I have M times L plus M squared is greater than or equal to 0. Right, and I'm going to just going to plug A in there. Also, L minus M times A is greater than 0. Because this L minus M is big, and the A is nef, nef and non-trivial. Right, and so therefore this holds, and this means L squared greater than M squared. It's strictly greater than M squared. Right. So as I said, I get a headache when I think about this, but there are, one way out of the headache is to divide into lots and lots of subcases. If Lm is less than 0, right, that might be possible, then we have L squared is greater than M squared, is greater than minus Lm. So that's just this line here. And this is greater than 0. And this is just a contradiction. Yes? So, this Lm squared is the same as minus Lm squared. And then minus Lm squared would have to be strictly, maybe that's greater than or equal to. Maybe the Lm squared would be strictly less than L squared times M squared. So if Lm equals 0, I think you get more or less the same thing. Right? So I don't think so we get the same contradiction, except possibly, except M equals 0. So why is this impossible? Well, it's sort of one of these things that's on the boundary of being possible. If M is 0, then this map here is an isomorphism. Right? This is the inclusion and multiplication by the divisor M. If M is the 0 divisor, it's just multiplication by the identity. Right? But that means that this extension is split. So then M equals 0 means OS of L maps to OS of M, OS of A is an isomorphism, so the sequence is split. So, you know, this is a case where, I mean, there's a contradiction, but it's a contradiction to an earlier assertion. It's not, you know, this is sort of on the bounds of being possible. Okay, and so that it's quite possible that this argument can be tidied up and that we don't actually need all three of these bullet points. But so that's an exercise. See if you can find a better way through this logic. So if Lm is greater than 0, so let's calculate C2. By the vertical sequence, right? And so I told you the C2 of E is L times M plus IZ. Right? But C2 of E is 0. So this one's greater than 0, and this one's equal to 0. So that's the proof of this result. So as I said, you know, in around 1976, I circulated this paper about Bogomolov's theorem, and Mumford made some comments on it, including this. Then about 15 years later, a guy called Igor Reid, also collaborating with Fedor Bogomolov, said, you don't have to apply this. You don't have to apply this for this H1 of A. You can also apply it to other H1s. So this is Bogomolov-Reid trick. And so, you know, it's basically just the same argument. Let me try and say what the statement is. So if A is nef and A squared is greater than 4, and P is in S, then P is a base point of Ks plus A, implies that various special things that I haven't had time to think about carefully, but implies that P is on a curve gamma with A times gamma less than or equal to 1. So, in particular, if Ks is nef and big, then and K squared is greater than 4, implies that 2Ks is free. So this is the same as the Bombieri base point free theorem. So this is half of the Bombieri theorem. Right. So this is corollary 2. Basically this point being a base point is also to do with some h1. And you interpret this h1 as an x and run basically the same argument. I mean, some of the details are different, but the argument's exactly the same. The heart of the argument is exactly the same, and even those getting contradictions in lots of small cases is the same. So corollary 3, and this is not the full strength of the theorem, but I'm doing it. If A is A is nef. No, I'm sorry. A is nef, and A squared is greater than 8, and P, Q are in KS plus A. Sorry. Distinct points. I don't want to do this. Let me just say. So if I want to have A is, I want to take KS nef and B. Right. So I want to be in the situation where we've got a minimal surface of general type. And I have A is R times KS. And I'm thinking that R is 1, mostly 1, but the same things will work in some other cases. Right? So if A squared is greater than 8, and PQ in S are distinct points, then A plus KS, so this means R plus 1 KS, especially 2 KS, separates P and Q, except for the case that P and Q are contained in some curve C. Let me contained in some E, effective divisor. And either A squared, either E squared equals 0, A times E equals 2, or E squared is minus 1 and A times E is 1, or E squared equals minus 2, A times E equals 0. So this case here, A times E, A is a multiple of the canonical class. So here I've got curves with K times E equals 0. So any curve like this, or any bunch of curves like this, is a bunch of minus 2 curves. And so this is the possibility that P and Q lie together on the same minus 2 cycle, and then the canonical map is going to contract them to a point. So the canonical map certainly doesn't separate them. Right? So these two cases happen only when R is equal to 1, and this is the case where there's a curve of genus 2, and the points P and Q are on that curve of genus 2 and are in the G1 2. So again, the canonical curve certainly doesn't separate them. And this is a similar case with 2 points on the same elliptic curve, right? So these are cycles, they're possibly singular, possibly even multiple components, but the idea here is this is a rational curve, this is a curve of genus 1, this is a curve of genus 2. Right. So in any case, you know, you don't really need to worry about the details. There's a method of arguing here which is very strong, and you know, given a method of argument that's very strong, obviously the people who've thought about it and have written out the proofs correctly. Okay, so let me just start the argument again. So proof. So this statement. So I have where am I going? I'm going OS of KS plus A. Here I'm going MP times OS of KS plus A. Sheaves on S, maximal ideal times this thing we're trying to prove is base point free. This is going down to one-dimensional sheaf supporting on the point P. So let me write KP. If I choose a local basis of this sheaf at P, this is just a residue field. Right? And so I have, the thing I'm worried about is H naught of this guy maps onto H naught of this, and that's equivalent to H1 of this mapping into H1 of this. Right? So suppose that H1 MP times OS of KS plus A not 0. Yeah, so this is dual to X1. So I can write the same sheaf there, MP times OS KS plus A, and then I can write omega S there. Or I can say this is the same thing as X1 of MP times OS of A, and then this omega S just becomes OS. So this is just twisting. If I twist down both of these by the same amount, it doesn't change anything. Okay, so now this is I could save myself trouble by just using the same diagram again. It's probably spoils things for taking notes. So anyway, this gives a sequence. 0 goes to OS, goes to vector bundle E, goes to MP times OS of A. Right, so an X1 is a sheaf like this. So locally at the point P, this has to be O plus O, and this has to map to O here, mapping by XY, so that it maps onto the maximal ideal. Right, now you can probably make a story like the story I made earlier about calculating the H1 by a check cocycle. But let me just leave it at this. This X1, you know, it's a derived functor it's a derived functor, and you can think of it, you can derive this by taking a projective resolution of one of these guys, messing around and so on. Or you can read some statement in homological algebra. Right. So in any case, the point is, this point, another way of saying this is, this point here does not impose linearly independent conditions on the vector space H0, the vectors on this linear system. So normally this linear system doesn't always pass through the point P. That means that I can evaluate this map here, and there's an evaluation map which has rank 1. So if that fails, there's some co-kernel here, and there are various ways of finding this this sequence. You know, this is you can also describe this in 19th century terms without using homological algebra. But let me just leave it at this. This is so I'm going to draw this diagram again. And so, you know, what do we know about E? It has C1 equals A, and C2 equals...
Or can you prove that E is locally free? You have an element in this extension, which is just a current shift a priori.
Yes. Yes, okay. So, you know, the MP, so, you know, as sheaves over a local ring, as modules over a local ring. Yes, in fact, you know, I'm as modules over a local ring OSP. Right? There's an X1, so over this local ring of this sheaf, the maximal ideal P. I don't need to write this OS of A because this is trivial in this context. OS P. This is one-dimensional, and it's based by the Godeaux complex. Right. So as extensions of local rings here, there is the trivial extension, where this thing here looks like O direct sum the maximal ideal. Right. And there is this extension. Right. So why can't this E be locally the trivial extension? Well, if it was locally the trivial extension, then it would map injectively there. Right. So I should say, suppose that this map here is not surjective. Suppose the map from here to H1 OS of KS plus A is not 0. Right, so I take an element here which is not extendable to a... So where this... You know, so I'm saying more or less directly this is not locally isomorphic to maps to MP. Right?
Yeah, it would be something else which is not direct something.
Locally there's only one extension.
Locally, yes.
Right? So either the extension is locally the trivial extension, or it's locally the Godeaux complex. Yeah. Right? And so I'm here. If it were locally the trivial extension, then I could just fill in the MP. I could write this O plus O and write this. I get a vector bundle here, but that would mean that this class comes from here. Right. So I mean, you know, we're working in characteristic P, and we have Godeaux vanishing. So this group is actually 0. Right. So I told you how to calculate C2 using an extension here, and so you know, there's I'm supposed to, if I want to calculate C2, I'm supposed to take C1 of this guy times C1 of that, which is an easy calculation. 0 times anything is 0 plus 1. Right. And so we're in the same business, exactly the same business as before. So C1 squared A, C1 squared is A squared, and that's greater than 4. This is the assumption. So this argument doesn't start working if A squared is equal to 4. Right? This argument is strictly when A squared is strictly greater than 4. And so therefore it's greater than C1 squared is greater than C2 for C2, and so Bogomolov instability applies. Works again. So it gives us, so here's the construction. And here is the construction that comes from the conclusion that comes from Bogomolov instability. Okay, and the argument's more or less the same. So this map here, this map beta is non-zero, right? Because otherwise, the L would have to be contained in O, so the L is less than 0, and that contradicts that L is greater than 1/2 of that E. Right, and so beta is multiplication by the equation of M greater than 0 and M contains P. Right, so this is the inclusion from a line bundle to a line bundle, so it's multiplication by some effective divisor, right? But in order for it to go into the maximal ideal here, times the OS of A, it means it's not, this multiplication map is not locally, does not maps to something which is not locally a basis at that point P, and that means that the ideal where the equation that we're multiplying by vanishes at P. So I'm rubbing off the argument which I'm just going to is equal to A, L squared minus M squared is greater than 0. Right, this is L minus M, which is supposed to be big, times A, which is supposed to be less than big. And then L squared minus 2LM plus M squared is also greater than 0. And, you know, you can't do this argument without the L squared M squared less than or equal to Lm all squared, the index theorem. So I think I'm going to just write out the same argument as before. If Lm happened to be less than 0, then we'd get L squared is greater than M squared is greater than minus Lm. Right. So this is still the same thing. This is A times M is greater than or equal to 0, because A is nef and M is effective. Right, and this is a contradiction. And L times M equals 0. Well, just worry about it a bit for yourselves. Don't. It's not. You know, it's a sort of a limiting case of the previous guy. Lm greater than 0. What happens if Lm is greater than 0? Well, calculate C2 of E using the vertical. Extension. So, you know, we know that C2 of E is equal to 1. But on the other hand, this is supposed to be Lm plus the degree of Z. Right? And we're assuming there's a case assumption that Lm is greater than 0, and so this is 1 and this is 0. No, I don't understand my notes. So if lm squared is 1, if lm is 1, then lm squared is less than or equal to 1, and you know, these two guys can't both be positive. So we can't have L squared greater than m squared is greater than 0. And so one of these, so this one here is, we're not allowed to have inequality here, and so therefore m squared equals 0. So what happens if m squared is, so what? Remember, I also make this assumption that A is equal to r kx. So if r is equal to 1, this would imply that, so m squared equals 0 contradicts that, so m squared equals 0 would give, m squared equals 0 would give ks times m equals 0, so m squared is equal to 1, so m squared is odd. Right, and this is contradiction. Right, and so the remaining possibility is that m squared is less than 0, and that's the conclusion. That, well, you know, I mean, I've already got this conclusion. I've already got a times m. This is a times m less than or equal to 1 in my argument. Right. So in any case, the conclusion is that in this, so for 2k, we'll just apply this argument with a equals kx, and then this k times m equals 0, k times m equals 1, and so on. They all give contradictions. Okay, so let me leave it at this. I've got a second talk to give later, and I want to think about that for a moment. Right. So you know, you can imagine just doing exactly the same argument for p and q. So I do p and q. What's the difference? I get p maximum ideal p, maximum ideal q here. Right, and then, you know, again I have to take an extension here, which I have to assume is non-trivial at both of the 2 points. So in other words, the point P and the point Q separately are not base points, but they get identified by the map K. and then you run the same argument with the same, basically the same conclusion here. And the only difference here is that here I get slightly bigger numbers. Right? And so I get slightly more possibilities for exceptional cases. Right? And, you know, these exceptional cases do happen, and they happened also in Bombiere's argument, also in this Catanese, Francesi, Hulick, and Reid argument I gave. And so you get... So in any case, you know, I've been talking now for maybe something like 5 weeks around this Bombieri embedding theorem, and I've explained there are 3 quite sort of technically different flavoured arguments for doing them. They're all interesting in their own way. Okay, so I want to talk about the Bogomolov-Miotka inequality in the second half of today's talk.